All right. Elliot, let's start with you. Tell me what an oscillation is.
It's basically the same thing as a vibration, so like repeating something from motion about equilibrium position.
Good. So it's like a vibration. And if you think about what vibrations are objects kind of shaking back and forth. And that's what this is. So it's repeating back and forth motion. To and fro is what the book says, but either way obviously is fine. About some equilibrium position. Okay, there are three important parts to this. There's actually a fourth I'll come back to, but three important parts to this. So first of all, it's repeating, so it has to do it over and over and over and over and over and over again. If it does not do it over and over and over again, then it does not count. Okay, has to do it over and over again, has to be consistent. Second, it needs to be back and forth. So it needs to go from one side of the motion to the other and then back again. Okay? So it has to have like a forward and a backward motion. You can't have just one. You've got to have both. Yeah?
What would be an example of that?
Pendulums and springs. Those are the two we're going to do this unit. But we're also going to talk about waves. So like water waves. So think about water waves. The water goes up to like a wave, and then it goes down to like a lower value and then up. So it's repeatable, goes up and down and up and down, and it's back and forth, well, in this case, up and down. And there's an equilibrium position. So like if the wind stopped blowing, the ocean would get flat, and that would be equilibrium. All right, so let's talk, and then some equilibrium position. So let's talk about what equilibrium is. Keegan, what do you got for that one, for equilibrium?
Oh, me?
Yeah.
Like in general, it's like a state of balance.
Yeah.
And then like no net change on the energy occurs.
Yeah.
And it's also a state in which no net forces and no net torque back.
Yep. So it's like a balance point. And it's a balance point for everything. Like it's a balance point in the energy. The one that I really focus on is the net force is 0. So at that point, the net force is 0. That doesn't mean the total force is 0. There is force on it still. But the net force is 0. So if you added all the forces up, you would get 0 for the total force. Everywhere else in the motion, there will be a force. Something worth mentioning, the force is not going to be constant in this unit. This is the first unit where that's true. Every other unit, our forces have been constant. So it would be the same force pushed or pulled or friction or whatever the case may be. This is the first unit where that's not true. In this unit, the force is not going to stay the same the whole time. Now, that's not going to be a problem for us because we're generally only going to look at equilibrium and at amplitude, which we'll get to here in a minute. So the fact that it is changing is not going to bother us because we're not doing calculus. If you were doing calculus, then it would matter because it would change as you change. So it would be a double integral. It would be a rate of change of position and rate of change of force as you change time. So it would be a dxt. It would be, what would it be? dx df over dt. So gets kind of gross, but we're not going to worry about that stuff too much. All right, Seth, what you got for period C?
The time required to complete a single cycle.
Good. So time required. I'm going to use oscillation since that's the key term. So time required to complete one oscillation. Now, the key word is this is a This is a time, so the unit is seconds. Unit is seconds. So it's how long it takes to go back and forth. Okay? And that is one complete oscillation. So if you think about a pendulum that swings from side to side, it's not from one side to the other. It's from one side to the other and then back again. Okay? So it's not just one side to the other, it's from one side to the other and then back again. Okay? Jay, what you got for amplitude, D? Good. So it's the maximum displacement from equilibrium and again, as she mentioned, it's either side of equilibrium. So, if you think about a pendulum, okay, here's my pendulum attached to some ceiling or whatever, okay, here's my pendulum, here's the bottom of the pendulum, it's called the pendulum bob, believe it or not, and here's equilibrium, so the balance point. So the balance point where the net force is 0 is straight down on a pendulum, okay? Amplitude would be this distance. Amplitude would be how far it is from equilibrium to where you pulled it. And it would be the same on the other side. So it's not just one side of the motion, it's both sides of the motion. And they should be the same value. So the amplitude from one side to the other should be the same, no matter which side you're looking at. Okay, so no matter what side you're looking at, should be the same. Good. All right, so let's look at restoring force. This one I'm going to do with y'all. So restoring force is the force that brings an object back to equilibrium. So it's the force required that brings an object back to equilibrium. So it's the force that acts toward equilibrium. And it's responsible for this oscillating motion. Okay, so it's a force that acts towards equilibrium and it's responsible for oscillating motion. Two quick things to add to this. One is it must be present for this to happen. You cannot have oscillations without a restoring force. It will not happen. You have to have a restoring force in order for that to happen. The second thing I want to mention is that it's similar to centripetal force. So on centripetal force, we said that motion around a circle was caused by something else. It was caused by tension or gravity or applied force. But we called that centripetal force when it made it go in a circle. The same is true with restoring force. So restoring force is caused by tension, gravity, etc. But when those forces cause an object to oscillate, we call it a restoring force. So the restoring force is not like a new force we haven't talked about. It's just a new application of the forces we've already talked about. Okay? So that's what restoring force is. I want to add one more thing, and then we're going to do the last part for today. And that is, I want to go back to oscillation. So we said it was repeating motion back and forth about some equilibrium position, it's caused by a restoring force. Without a restoring force, it doesn't happen. So these are the things it has to have. To be simple harmonic motion, it has to be repeating, it has to be back and forth, it has to have equilibrium. But you should also know what causes it, and it's caused by a restoring force. Okay? If there is a restoring force, it will cause it to do this. And the examples we're going to be looking at for this unit are pendulums and springs, but there's lots of other examples because we're also getting into waves this unit as well. Okay? All right, go ahead and put that off to the side, but I wouldn't necessarily get rid of it all the way. And take a look at the lab sheet. So this is going to be a really big lab. Part of it is you guys are going to design it, and we're going to start from scratch. Like, I'm not going to tell you what to do. We're going to figure out what to do. The second thing is it's going to take us a lot of class periods. So it'll take us at least to Tuesday to finish it. So it'll be a good long haul on that. So just kind of